While each pattern of additions, transformations, transfers, and losses is unique, soils can be classified into general categories based on the conditions under which they form. The authors state that ecosystem differences in additions, transformations, transfers, accumulations, and loss give rise to distinct soils and soil profiles. Now again, here's figure 3.11, and this again is a generic soil profile showing the major horizons that might form under given conditions. When we talk about how there's an O horizon, which is an organic horizon, that we'll sometimes see in soils, or an A horizon, a B horizon, and a C horizon that form above bedrock. And sometimes there's even an E horizon. Now, not all soils have all these horizons. Not all horizons are the same depth, nor are they made of the same chemical constituents. And the different patterns that we see in soil horizons and their characteristics give rise to what we call soil orders. Now, soil orders are a classification system, and in the US there are 12 major soil orders that are recognized and are found in different places. All of the different soils end in SOL, a sol. And so on one end of the spectrum, you see that there are entasols. What entasols are soils that don't have any well-developed horizons. So you wouldn't actually characterize an O, an A, a B, and a C horizon, for example. And this is where you would have sand deposits, for example. So a big sand dune wouldn't have those horizons. It would still be considered a soil, but it would be an entasol. Just below that, you have inceptisols, which are weakly developed horizons, and these are young soils. And then there's a whole series of other sols that we have. Histosols, which are very organic, that you would find in a bog. A gelisol, which is typically the types of soils that form above tundra. And then andisols, which are recent volcanic areas. Iridosols, mollisols, vertisols, alphasols, spodosols, ultisols, and at the other end of the spectrum, oxasols, which you find in underneath tropical forests in places that are very hot and humid. So again, when we took a look at Mount St. Helens, this would have been considered an andesol. You're not seeing much horizons because there just hasn't been time for soils to develop, and this is just all material that came down from the volcano and layered on top of one another. So there really hasn't been any horizon development there. At the other end of the spectrum, we have this oxasol, which are really deep, for example, and made of highly weathered material, such that all that's left are really the insoluble precipitates of stuff that's just really hard to lose. There's a general pattern by which these soils are formed. So we talked about how an entasol is generally what you start with before there's really any weathering that occurs. And then from the entasol, depending on the conditions, if you have a relatively cold system with permafrost, you'll generate the gelisol. If it's a waterlogged soil, it's a histosol. Volcanic entasols we think of as andisols. And sometimes we have something called a vertisol, which has a lot of swelling clays in it. Once weathering begins to happen, we get to this inceptisol. And in dry areas, deserts, they become iridosols, but in grasslands, we tend to think of them as mollisols. And they have different sets of properties under a grassland that you would get under a desert. So for example, when we had looked at caliche, that was in an iridosol, and that's something that really only forms under deserts. As we go through here and we're into relatively moister conditions, you can generate an alphasol, which is kind of a deciduous forest soil. Then under really warm or hot conditions, you go to an ultisol, and then eventually an oxasol. And that's when you have a lot of leaching, and you have to be in a hot, wet place with soils that have been in place for a long time. So this degree of weathering and soil development gives you soils that are associated with not much weathering all the way to very strong weathering and very high degrees of soil development. The authors give a couple examples of some typical profiles of 5 of the different soil orders. So for example, here is a gellisol, and that's a tundra soil, you're going to have an O horizon that's relatively deep, lots of carbon there. Then you tend to have a relatively shallow A horizon, C horizon there if you do, and then often permafrost. And sometimes you won't even have the C horizon, you go right into a permafrost, which is just these soils that would have been very similar to an O or A horizon that just became frozen as new material piled on top of it. In contrast, there's an aridosol, which isn't going to have a lot of organic matter because decomposition is going to be high. And then you'll have this calcic layer. And we talked about the caliche that you can get in an aridosol. A spodosol is different, where it's a really acidic soil that forms under conifer forests. You have an O horizon of decomposed material and an A horizon, and then here's where you start to see an E horizon, where you get leaching of material and then redeposition down here. After that, they show two examples after that, which is a mollisol, and this is that grassland soil. And they put deciduous forest there, but really mollisols we think of as grassland soils. And you have this really deep A horizon, not quite as high carbon concentrations as you would get in an O horizon of a tundra, but these tend to be pretty black soils. And again, 50 centimeters is not unreasonable for a grassland for this A horizon. And then by the time we're into an oxisol, you can see you have over a meter of relatively well-weathered material. Sometimes it could be 5-10 meters like we'd seen before. And this is all considered A horizon, and almost no O horizon to speak of at all, because materials in wet rainforests, tropical rainforests, decompose relatively quickly and just don't stay around long enough to form that O horizon. Lastly, they show some of the different soil orders, looking at them by moisture and temperature. And you can see on the x-axis here we have temperature, so cold places, warmer, hotter places. This could be mean annual temperature. And when you have a mean annual temperature that falls below 0 degrees, you tend to get permafrost below the O horizon and the A horizon, and this gives rise to the gellisols, those tundra soils. When you're above 0 degrees, you're not going to get permafrost, so you're not going to get gellisols. And the pattern of soils that you get depend on how hot it is, but also the moisture. So dry places give you aridosols. Mollisols tend to be in grasslands, which are in drier areas and forests. And then we have these different types of forests that you're going to get depending on the temperature. Alpha sols in forests that have moderate temperatures, moderate moisture. Spodosols in relatively wet places. Then when we get to really hot and wet places, these are the oxisols. That's just a general overview of some of the major soil orders and where you find them. The specific soils that you find in a place depend on all the state factors that are going to be present and a lot of other things, but it's good to know what the basics are. And if you can understand the basics of some of these major soil orders and what gives rise to them, you're in pretty good shape for understanding soils.